So I want to say a few words about synthesis of control strategies for interconnected system under uncertainty. This is work done by my student Kasra. And as promised, I'm going to try to keep it a bit short, and maybe you can bring the whole session a little bit back on time. There are many systems out there that motivate this work. Starting from the bottom, I'm showing here a team of unmanned aircraft. They can communicate locally with each other based on Euclidean distance, and the goal can be, for example, optimal coverage of a certain area. Here I'm showing a power system where the subsystems locally communicating with each other might want to optimize for storage or delivery of energy. An example that you saw a lot during the previous talks, autonomous driving. Think of a smart city where autonomous cars talk to each other, and also with smart infrastructure such as smart traffic lights in order to optimize traffic, in order to minimize congestion. At the bottom, I'm showing a warehouse robotic example, and realistic models for such systems are have uncertainty. And uncertainty can be caused by model dynamics, can be caused by disturbances like wind in the case of the flying aircraft, rough terrain, and so on. And another twist that I'm adding here is the fact that we're requiring such systems to satisfy rich temporologic specifications. And what I'm showing here at the bottom very much resembles what Jonathan just talked about. He gave a comprehensive introduction to a logic that's also relevant for this talk, which is signal temporal logic. So rather than just requiring agents to go to specific goals, I want to be a bit more expressive, give agents choices to go from one place to another. And in this time, the specification is also time concrete, which again makes a connection to STL that Jonathan just described. Formally, this is the problem that I'm looking at. A collection of interconnected dynamical systems, continuous time, discrete space. We assume they're linear for simplicity, and for computational reasons, they're going to become obvious later. If we stack all of them together, I'm going to use this notation for the aggregated system. The interconnection between the system is through dynamics. There are some systems that the state of some systems appears in the dynamics of system J, in this case appear in the dynamics of system I, also interconnections through controls. The controls about the systems can show in the dynamics of the below. Because I'm shorter than the previous speaker. Yeah.
Okay.
And then there is noise, there is uncertainty specific to a specific system I. So the goal is, so we're starting, we know the initial states for the systems, for the individual ones. The goal is to bring them to individual goal regions, assuming that the individual uncertainty are within known bounded sets. There are constraints for the state and control for each subsystem. I want the controller to be decentralized, which means I want control for system I to be only a state feedback controller of the state of system I. And in addition to that, I want to be able to satisfy those type of rich specifications, right? So again, I'm talking here about STL that you just saw before. I want to minimize the cost. We assume for simplicity here that the cost is actually decoupled. So the overall cost is a sum of cost of individual subsystems. And also for simplicity, I'm assuming that the costs are quadratic in state and controls. So before looking at this problem, I'm going to look at a simpler problem in which there is no STL spec. So the goal here is to just drive each system to its own goal region while satisfying state constraints, control constraints, and the assumptions on the disturbance and minimizing the cost. And so this is, I mean, most of you are familiar. This is actually a very popular problem, very well studied. There's a large amount of work. I'm showing here very, very thin subset of related work. And without spending time here, I just want to emphasize that what kind of sets this work apart is that we have a couple of dynamics, temporologic specifications, and we look for fully decentralized controllers under the face of uncertainty. Very briefly, our approach is what we would call a divide and conquer approach, in which we make this very strong assumption that everything that's not part of system I, we're going to dump it into one large uncertainty term. So the coupling through the state of the other systems, coupling with the controls of the other system and the individual disturbances, I'm just going to put it into one bounded disturbance. In this way, the systems become decoupled, and then the question is, can we solve the problem by just keep on adjusting this set? So very briefly, what we're going to do here, we're going to have a tube-based approach in which I'm going to keep track of the possible set of states, which are called viable sets, corresponding control sets, and then formulate assumed guarantee contracts. So this kind of assumption that system I makes is obviously going to be based on what the actual other systems connected to systems I do. So there's going to be obviously some circularity reasoning that you have to deal with. And the question is, can we eventually converge to the right assumptions which are in agreement with the actual state of the other systems, and ensure that eventually each system goes to its goal while satisfying the state constraints, while satisfying the control constraints. I think the two main contributions that Kasra had in this couple of papers that the presentation is based on is coming up with a certain parameterization for all the sets that we have to deal with, which are zonotopes. And I guess most of you are familiar with zonotopes. They're very convenient to use when we have to do Minkowski set sums, and when you deal with the linear maps, because it's very, very easy to construct the image of a zonotope through an affine function. And the other ingredient that you have in here is a certain potential function over a certain parameterization of the problem, which ensures what we call correct composition. So which kind of takes care of this circularity, which is the main problem whenever you have assumed guarantee contracts among systems in a multi-system problem. So again, I'm going to try to keep it short. So this is the kind of the structure of the rest of what I want to show. I'm going to first look at the problem for just one system, right? So rather than having a collection of systems, I'm going to look at one system, which can be seen as the aggregation of the individual subsystems that I showed you before. So this is the problem that I'm showing here. I'm going to try to get rid of this thing and move it somewhere. Okay. This is the optimization problem that we're focusing on, where, as I said, the cost is actually a sum of individual costs, which can be quadratic. To simply try to understand how complicated this problem is, we can try to start with some simplifying assumptions. Like, for example, at the beginning, if there is no control, then this problem can just become a large QP that you can solve and then easily get a solution, right? And then the solution, and I wanted to also note that in both the state and the control are optimization variables in here. So the dynamics of the system actually becomes part of the constraint of the QP. Obviously, when you have noise, obtaining such an open loop controller is not a good idea. What you want is a closed loop controller. If you try even a very, very simple state feedback controller, the problem becomes non-convex because you have to optimize both the entries of X and the entries of matrix K are optimization variables. There is a product in there, so the problem becomes a bit more complicated. So, so when you have noise, roughly there are two main approaches to deal with this problem. One is based on min-max. This is like a worst case scenario with respect to noise. So first try to find some expression of omega by solving this optimization problem, which is going to be a function of X and U. And there are a couple of papers, actually more than a couple, but I think the common denominator here is that solving this problem is difficult. Finding omega such that you can formulate the second optimization problem, which is a minimization problem. More popular approaches use what's called tube-based optimization. So rather than just trying to find an optimal trajectory, make a sequence of states, people work with sets. So the question is, can I formulate this, which are sets which are ensured to contain the actual state, and these are called viable sets. So you're going to have dynamics for such sets, and then you have to do some mix. So if you work with sets rather than individual states, you might have to have some adjustments and approximation to the cost in here. Look at, for example, come up with some sort of centers for this, so the cost would be a bit modified here. So solving these problems, the main challenge here is to deal with, again, the size of the problem, because so all these sets are usually polytopic. And then when you solve this optimization problem, you have to optimize over a parameterization of these sets. And if you use age or V representation, you can end up with quite complicated problems. So one way to deal with this, which we proposed some time ago, is to use zonotopes. Very briefly, zonotopes are described by centers and generators. So if I have a zonotope which has a center and a set of generators, which are the columns of this matrix, then we have the advantage that we can easily construct the image of a zonotope through an affine function. You literally just reconstruct the center and the generators. And Minkowski sums are also very easy to compute, which is the main problem if you have different parameterizations of polytopes, such as age or V representations. And again, very briefly here, I'm going to show here a solution of the problem that I showed you before, which is basically made of two steps. First, solve a large QP in which we optimize over finding zonotopes for the viable sets and the control constraint and the control sets at every time point. So this is, again, one optimization problem that's solved offline, which gives centers and generators for the zonotopes, ensuring that the state stays in there for all times, and also centers and generators for the zonotopes at every time, which contain the control at every time. And after this problem is solved, we can show that you can solve online at every time an LP, which gives you a control as a function of time, which can be ensured to stay inside the zonotope that we find at the previous step, which in turn ensures that the state stays inside the viable set that we found when we solved the QP. I know I'm extremely high level here, but again, all I want you to remember is that if I just have one system and I want to solve the problem that I showed you before, it can be mapped to solving offline a large QP, followed by online a lot of LPs, if you use zonotopes. So now what do we do if you want to deal with systems which are decentralized? Can we make the problem computationally more efficient rather than just aggregating everything into one system and solving a large optimization problem? Am I keeping my promise and I'm going faster, Glenn? No. Okay, no, I want to keep my promise and I'm going faster. So again, remember what I'm going to do for each subsystem. The easiest way to decouple them is to just use the, actually go here. Just use the constraint sets that we have for the states and controls and all possible disturbances which are given for every subsystem, and then do this decoupling, and then just solve the problems separately, which is, it's perfectly correct, right? There is no notion with correctness there. The problem is that the solution is extremely conservative, because assuming that this is just going to be, was taken into account the whole initial constraints that we have for state control and disturbances might be way too much, because when the systems start interacting with each other, those can actually shrink a lot and you can take advantage of that. So then the idea is to somehow, so we define this notion of compositional correctness. So at every time step so we're going to have an iteration. At every time step, we're going to make an assumption about, trying to keep my promise without becoming too sloppy. If I can do that very quickly. Equation here. Oh, this one. Okay. So rather than having, this like very, very rough decoupling where we consider the constraint sets in here. What I'm going to do, I'm going to design an iterative procedure in which we consider actual constraint sets. These are the viable sets, actual constraint sets for states and controls. And then at every iteration, looking at the viable, the viable sets for states and controls, and construct actual sets for this whole coupling part. And then hopefully converge to a situation in which the assumptions that a system makes about this part is actually included into the what this part actually is, when these sets here are actually replaced with actual viable sets and sets where the controls are. Am I doing a good job being sloppy and high level? Okay. So in order to do this, we make the problem a little bit more complicated. We actually add a potential function, which more or less, so this is the original optimization problem that I showed. So what we do, we define a notion of distance between the assumed and the actual disturbance sets, and use this distance as a potential function that we include in the cost, and we're going to have some extra constraints. And we can actually show that if we modify this problem, so there's three ingredients right now: is the zonotopic parameterization of the sets, and then there is this function which comes on top and kind of adjusts the optimization problems with the guarantee that if the potential function goes to 0, then compositional correctness is ensured, in the sense that the assumptions that the system make about the system that it interacts with are actually correct. Meaning that the actual states that those systems are in is consistent with the assumptions that the current system makes. Okay, and then I can show you examples. So maybe this I can make it a bit quicker. So this is a simple system made of 4 two-dimensional interconnected systems, and this basically movie kind of shows you the main idea, where there is an iteration at each time step. Those the green zonotope shows the viable sets, which keep on adjusting, and eventually they become enclosed at the final time into the goal sets, which are the blue rectangles, those squares in this case. And what we can show, and that's actually I think the most exciting part of this work, is that this method scales. So if you try to make a comparison between solving the optimization problem where everything is centralized, versus taking advantage of the fact that you have this local interaction between the subsystems, you can get a huge increase in computational efficiency, right? So this is basically, it's a large system made, I think, of 100+ subsystems, all of them two-dimensional, and this is how the computation time scales, which is a orders of magnitude better. And again, we can talk more about this. I promised at the beginning I'm going to show something with STL, so I'm just going to make the problem a little bit more complicated by, in addition to requiring the systems, each system to go to a goal, I'm also going to have some more correctness requirements. And I guess most of you are familiar, most of STL, people familiar with STL are also familiar with the fact that if I have an STL formula over linear predicates, then Boolean satisfaction of that formula can be mapped to the feasibility part of a MILP. Literally, for satisfaction of predicates, you introduce binary variables, and then you can think of always and always operators as being conjunctions over satisfaction of predicates. You might remember that conjunctions can be mapped into MILPs by just because conjunctions are minimum functions. And okay, so I guess most of you are familiar with this. So that's basically what we're doing here. We take that STL and map it into a chunk of a MILP, which we add to the constraints of the problem. And in the paper that we wrote recently, we showed that if you just do that, you can end up with a problem that's infeasibly large. right? This embedding of an STL satisfaction to a MILP is actually, it can lead to hundreds of extra variables, which can make the problem very complicated. And then what we do in this paper, which we don't have any formal proof that it works perfectly, but it's intuitively what we do in here is we enforce the satisfaction of the STL formula for the nominal systems where there is no noise, and then look at what predicates are satisfied, and then when we go back to our original problem, we just use those predicates, and it can be shown that this more or less works, right? So basically, this example shows it's the same problem, the same system from before, but now we have an STL formula in there. And so again, what you can do in here, you can generate controllers which are decentralized. They satisfy the STL formula. They go to some goals. They satisfy polytopic state and control constraints. And they're computationally efficient in the sense that you can look at quite large problems and solve them fast. And these are the people who did the work. Thank you.
We have time for maybe 1 or 2 questions. All right, well, I have a question. So I guess in a lot of this work, you provide basically these bounded disturbance sets in order to actually derive these guarantees, right? Yeah. So I'm curious how you like calibrate these disturbance sets, and if there's actually a way that you can kind of choose them in a principled fashion for your type, for your application areas.
So again, we always assume it's polytopic, so we can, and then, yeah, just polytopic, but then being a disturbance set, you don't want to make any more assumptions on that. You want to deal with the way they are.
Right, but my question is more like, how do you choose these polytopes, I guess, in the first place that describe
the disturbance polytopes?
Right, yeah.
Just the disturbances, they come with the system, they come with the problem. I mean, our examples are fabricated, obviously, you know, we just took like very simple systems and try to scale up by just making hundreds of them, but you know, it depends on the problem.
Sure.
But they have to be bounded polytopes.
Sure.
That's all the only restrictions that we have.
Okay.
Yeah.
Do you think about the case where you have, I mean, where A and B, typically your matches are also like polytopic, given by polytopes, for example?
Oh, they're being uncertain too with
Yeah.
polytopic entries, that would make the problem much harder. Much harder. You destroy the whole. I mean, you're going to have product type nonlinearities between the entries of A and your state, which is an optimization variable. Good point, but at least for now, you know, we assume the matrices are, you know, given. The only way you can have uncertainty is additive, and it has to be polytopic.
Okay. Because the multiplication of tools on the top is going to add new generators, and you don't want to forget those generators.